Hello math enthusiasts, welcome to MathGlider, where we glide mathematics right into your mind. Let us look at real numbers and sequences today. You know, the set of real numbers forms a field under the operation of addition and multiplication. So it has to satisfy some properties, some fundamental properties in order to become a field. These are all kind of properties which are required to become a field. First of all, we have commutative property. With respect to addition, the real numbers are commutative. That means if we add two numbers in any order, it doesn't matter. We add a plus b, it will be same as b plus a. Then we have multiplication. So in multiplication also order does not matter. You know, there are some multiplicative operations which are not commutative. But in real numbers that does not happen. If we do a into b, it will be same thing as b into a. Then we have associative property for real numbers. That means addition is associative. Like if we add a plus b first and then we add c, that will be same as if we add b plus c first and then we add a to it. And multiplication is also associative. That means if we multiply ab first and then multiply it by c, it will be same thing as a multiplied by b into c first and then we multiply a to it. We have a distributive property for real numbers. Distributive property says the relation between multiplication and addition. If we add b plus c and then we multiply a, it will be distributed like a into b plus a into c. The same way we can take common. If we have a factor in both the addition terms, we can factor out. We can take common a. This is the distributive property. Then we also have a property called identity elements. We have some identity elements in real numbers. So we have an additive identity. That means a number, when we add into that any number, it will give us that number back. Like a plus 0 is equal to a for all a. Then 0 we will call it as additive identity. What is the multiplicative identity? What is the number when we multiply by any number, it will give us the same number, it will be 1. If we multiply 1 by any number, it will give us the number back. So multiplicative identity in R is 1. Then we have something called as inverse elements. Inverse elements exist in real numbers. So what is the inverse element? The number when we if we are talking about additive inverse, the number we are adding in a and we will give us that will give us additive identity. That number is additive inverse element, additive inverse. So additive inverse of a is minus a. Like if we add a minus a in a, it will give us additive identity 0. Then we have multiplicative inverse, the number by which we multiply and we will get the multiplicative identity, which is 1. So a into 1 by a, you know, is 1. But a should not be equal to 0. Why? Because 1 upon a is not defined then. So we have some order properties in our real numbers. So you know, in the line of real numbers, order matters. Every element has some order. Every number is greater than or equal to some number or less than or equal to some number. So we can compare the real numbers. These are called as order properties. First property says that if we have a less than b, then we can add some constant on both sides. That is the first property. Like we have a here and we have b here and we add some constant to both the numbers, then a plus c will jump something like here and b plus c jump something like here. But then also a plus c will be less than b plus c. That is the first order property. Then we have, if a is less than b and we are multiplying some constant, then you should know that if C is positive, then the greater side remains greater, like A into C will be less than B into C. But you should note here also that if C is some negative number, then we will have to flip the inequality sign. Then A dot C, A into C will be greater than B into C. This is the second order property. You can ask what if C is equal to 0? Then both sides will get 0. Triangle inequality. We have a triangle inequality in real numbers. So you can see triangle inequality says that if we add two numbers and then we take absolute value, it is always less than or equal to absolute values of two numbers separately and then adding. Okay, this is obvious to see in 2D. It is similarly obvious to see in 2D also. This property is fundamental in metric spaces. This is like a very basic idea satisfied by all kind of distances in metric spaces. We also have something called Archimedean property in R. What is the Archimedean property? It shows the infiniteness of the natural numbers. You know, natural numbers are infinite. For any number, any real number you give, I can give you a larger natural number. That is Archimedean property. See here, for every real number x, there exists the natural number such that n is greater than x. Okay. So this property we need many a times to prove some theorems. Okay. So this property implies that no real number exists larger than every natural number. Like every real number you get a larger natural number. That means natural numbers are not bounded. We can prove that natural numbers are not bounded by the Archimedean property. That's what it is written here, that natural numbers are unbounded above. Then we have density theorems. Density of rational numbers in R. The rational numbers. You know, the rational numbers are what? The numbers which can be written in form of P by Q. We will call them rational numbers. And this set of rational number is dense in real number. What does it mean by dense? That means between any two real numbers A and B, there exists a rational number such that that rational number is in between A and B. That is the density theorem, density of rational numbers. Like on the real line, if no matter how close we take the points, we should not take a single point obviously, but if we take two different points, no matter how close they are, there is a rational number in between them. And when we say there exists one rational number, we can always say there exists another one, there exists another one. So we can say there exist countably many, there exist countably infinite rational numbers also. So there are infinitely many rational numbers between any two real numbers. This we can prove by density of rational numbers. That also means rational numbers are not isolated. Okay. So you can see if we take this set 1 and 2, 1 comma 2, this set is isolated. Okay. So 2 points are not arbitrarily close to each other. That means isolated. But rational numbers are not isolated. That means in between any closed open interval around a number, that whether that will be real number like a rational number or irrational number, in between the open interval around that point, we will get infinitely many, that means countably infinitely many rational numbers. So that is all for today. We will see a sequence of real numbers in next video. Till then, keep gliding through maths. And thank you for watching the video. Like, share and subscribe with your friends.